Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at group problem 7a, which is going to explore some of the connections between work and energy. Specifically here in our group problem, we're going to be looking at pushing an object, a lawnmower, getting it up to speed, and then letting it go, and seeing how far it travels, and using the ideas of work and energy to make a determination on how far the actual lawnmower moves after we begin pushing it up to speed. So I'll read a bit of the problem statement so it gives us a context of what we're going to do here, and then we'll get started. On a warm Saturday afternoon, your parents ask you to mow your lawn. With excitement, you jump off the couch, ready to help your parents in any way they need. Your parents let you know that if you help out, they will allow you to go see a movie with your friends later that evening. Score. To get started, you get the lawnmower, we're given a mass, out of your garage and begin pushing it toward the front lawn. Unfortunately, just as you begin mowing the grass, you trip and fall and allow the lawnmower to move forward. The lawnmower gets pushed forward and begins to move toward a flower bed in the front yard. Watch out. You hope there's enough friction to stop the lawnmower before destroying the flowers. Based on the information provided, determine if the lawnmower will stop before hitting the flower bed. So, before we do get started, as a reminder, there are keys available for the problem out on Canvas. If you'd like to access those, they are available to you. Here we're going to be looking at group problem 7a. Now, I'm going to start with a bit of a picture here just so I can get a visual. So here we've got our lawnmower. And assume we're going to be pushing down on the lawnmower. We're told we're pushing down at an angle of 30 degrees below the horizontal. We're also told that the lawnmower, we push a distance of 4 meters across the driveway over to where our lawn is. And then there's a flower bed. Just label that FB for flower bed, that way we don't spend too much time with the picture. And we want to know, we're told this distance is about 2 meters away. We want to figure out, does the lawnmower, once we get it moving, again, this is the point where we kind of trip, let the lawnmower fall forward. We want to know, how far does the lawnmower travel once we push it and let it go on the grass? We're told we have 2 meters of space, and we want to figure out, do we actually use that 2 meters? Does our lawnmower hit the flowers, or are we safe? So one of the first things that we're asked to do here is to begin by finding the work done on the lawnmower in this scenario, kind of the first scenario, getting the lawnmower up to speed. Now, in this first scenario, we're going to assume that initially we have no energy with our lawnmower. Assume it's at rest on the ground, and there are no springs really involved here, so we won't look at spring potential energy. We want to figure out what's going on with the energy maybe here and see how our energy is changing. So here's what we do know. We do know that the work done, this is one of the first things we want to find, how much work do we do on our lawnmower, how much energy are we giving our object. The work done is equal to our change in energy. Now, we don't actually know how much energy we end with, so we can't necessarily use this approach first. But thankfully we have another way of finding the work done on an object. And that work done is a product of the force applied on the object, the displacement of the object, and cosine of the angle between the force and the displacement. Now we are told that we apply a force of 65 newtons down onto the lawnmower. That's a value that we're given in the context of this problem. So we're told the force we apply is 65 newtons. We are moving the lawnmower 4 meters across the driveway over to the grass. And the angle between the force and the displacement, here's where we need to pay attention. We are pushing down the handle of the lawnmower like so. But the lawnmower is not moving down at an angle. The lawnmower is moving straight forward in the x direction. So here, this solid black line represents the direction of our force. This red line represents the direction of our displacement. And 30 degrees is the angle between the force and the displacement. It's the angle that touches both vectors. Right? We would not want to use this angle in here, we can assume that would be a 90-degree angle. We wouldn't want to use 60 degrees, right? Like this angle here, because that angle is not between the force and the displacement. It's between the force and the vertical here, right? The y direction, which our object isn't moving in the y direction. So here we're going to use cosine of 30 degrees. Let's take a moment and plug this in. Do make sure your calculator is in degree mode. Mine was actually in radian. Otherwise, that's going to cause us a little bit of an issue with the numbers we get. So 65 multiplied by 4, multiplied by cosine of 30 degrees, we get about 225.2 joules. So the work done, 225.2 joules. Now that number should be positive because our object, the lawnmower, is going from rest on the ground, no energy, to on the ground moving, so some energy. So there's a change in energy here, which means our work done should be positive. Now as we go forward, specifically the work done on our object is going to change our object's energy. We know that initially our energy is 0, so our change in energy, E final minus E initial, well initially our energy would be 0, because we're at rest, on the ground, no springs involved. Now at our final point, again this isn't the final point like over here by the flower bed, this is the final point right in here for the first scenario. We have to think what kind of energy our object would have. Now there are no springs here, so we can ignore spring potential energy. Assuming that we're pushing this just across the level ground, our object isn't going to gain any gravitational potential energy. So at our final point, the energy our object would have would all be kinetic energy. So our work done, 225.2 joules, is going to equal the kinetic energy of the lawnmower, at this final point, which is 1/2 m V final squared. Now final again, final means in the context of this part, as we move across the driveway. So we know, let's go 225.2 joules. It's equal to 1/2. We're told the mass of the lawnmower here is 40 kilograms, multiplied by V squared. Right off the bat, 1/2 of 40, that's going to give me 20. So I'll divide both sides of my equation by 20. So 225.2 divided by 20, I get about 11.25. Remember, that's equal to velocity squared. So then we'll take the square root of that value. And we'll get about 3.35 meters per second. So somewhere in the 7 to 8 mile an hour range. Maybe we were trying to get it going pretty quick. That way we don't have to spend too much time pushing it across the driveway. So now we've got our number, which is something we wanted to find. Now from here, this is where our object changes what's going on, or what the context changes a bit. Right? Initially we're looking at just getting our lawnmower up to speed. Now we're going to start to look at what happens over here. So, as you can imagine, when we get to this portion of our scenario, there's going to be some friction involved between the lawnmower and the grass. And our hope is there's enough friction to slow our lawnmower down before hitting the flower bed. So for kind of this second scenario, part 2 if you will, if we take a look at the forces acting on our lawnmower, well, we would have a force of gravity, we would also have a normal force, and if our lawnmower is moving to the right, that's the way we're pushing it, friction is probably going to act opposite of our motion. We'll call this kinetic friction, assuming the lawnmower is sliding to a stop. It's actually kind of rolling here, but we can approximate this to be a kind of a kinetic, sliding, rolling type of friction. Now we want to know what is that force of friction, because that will likely help us figure out what's going on with our object here. So looking at the context of our problem, we want to find that force. We might have to find some of the other forces here. We do have an equation for the force of friction, our coefficient of friction multiplied by the normal force. Let me look back at the context of our problem. Okay, we are given here a value for the coefficient of friction. It's about 0.3. Yes, 0.3 here. But we need to know the normal force. So if I look at the y direction, that's the direction in which our normal force shows up, mass times acceleration. Now our lawnmower is going to be accelerating here, but not in the y direction, just in the x direction. So mass times acceleration, if acceleration is 0, then mass times 0 would be 0. So I now set this up this way, Fn minus Fg, that is my sum of forces. I'm adding them up, but one of my forces is negative, so I would have to subtract those. So Fn minus Fg equals 0. I can add Fg over to show that my normal force is equal to my force of gravity, which would make sense here. Otherwise, our lawnmower would be accelerating up off the ground or accelerating down into the ground. And this is equal to the mass of our lawnmower, m multiplied by gravitational acceleration, 9.81. So 40 multiplied by 9.81 gives me a value for my force of gravity, which is equal to my normal force of 392.4 newtons. Mass of 40 kilograms, gravitational acceleration for the Earth, 9.81 meters per second squared. So now that we know our normal force, we can bring that back up here to find our force of kinetic friction. Let's do that. Fk, sorry, sometimes the board is a little bit sensitive to the marker. So our force of friction is our coefficient, 0.3, multiplied by our normal force, 392.4 newtons. So now we can find our force of friction, F sub k. We'll multiply these values together, we get about 117.7 newtons. So now we have a value of the force that is acting on our lawnmower. Now, something we could do is we could use that force, again with Newton's law now in the x direction to find an acceleration. We could use that along with our velocities to find our delta x, how far the lawnmower moves. However, there's actually another place where we have delta x. It's in our work equation. Let's think about what is going on with the work being done here in scenario 2. All right? So, here's what we could do. We could say the work done on our lawnmower is equal to the force acting on our object multiplied by the displacement of the object while the force is acting on the object multiplied by cosine of the angle between those two vectors. Now, we already actually know what the work thing is going to be here. Think about where we started. As we get our lawnmower up to speed, we did 225.2 joules of work on the lawnmower. As the lawnmower slows down, friction is taking away all of its energy, which means friction is going to do negative 225.2 joules of work. It's taking away all the energy that we added in. So we know the work value, it's going to be negative this, negative 225.2. We just solved for the force. We know the angle involved, so we should actually be able to find the delta x and see if it's under 2 meters. Let's try that and see what kind of result we get. The work done here would be negative 225.2 joules. The force causing this work to be done is our force of friction, 117.7 newtons. Delta x, which is what we want to find, and cosine of the angle between the force and the displacement. Remember, our force of friction is acting out to the right based on our picture, but our lawnmower we drew as, force of friction is acting to the left, I misspoke. Our lawnmower is moving out to the right. So, lawnmower moves to the right, delta x, force of friction to the left, F. The angle between those is again 180, which would mean that's going to help us work with the negative 225 over here. So I know cosine of 180 is going to give me a value of negative 1. So really what I need to do is I need to divide the right side of my equation by 117.7 and negative 1. So we'll divide by negative 1 and 117.7. Divide this side by 117.7. Those values will cancel out. And negative 1. Those values will cancel out. So now we'll take negative 225.2 divided by negative 117.7, and we get a delta x of about 1.91 meters. Now this value tells me, and sorry, sometimes the board is not like how I draw, I apologize, I do my best. But this tells us the lawnmower moves 1.91 meters as friction is doing work to slow down the lawnmower. Now we were told we have about 2 meters of space. This is slightly under 2 meters, so we have enough space for the lawnmower to be able to slow down. So here in our problem again, we're looking at the ideas of work and changes in energy, and using those to solve a real world type of problem. As we've seen very often, we can't just use one equation one time to oftentimes analyze a system like this. We need several equations that we can really piece together so that we can step by step understand how to solve a more complex scenario. But again, remember, as we're asked to find these different concepts or these different quantities, things like forces or work or energy or displacements, inventory the equations that we have. Think about what we know. There's usually always going to be more than one equation that we have, and we have to evaluate which equations best fit our scenario. Hopefully this gets you going in the right direction on group problem 7A. If you have questions, as always, you're welcome to direct those toward me, and you can also check Canvas for other resources and keys for this problem.